All right, we are going to start recording. So, if that's okay with you.
Yeah.
Okay, so here we are. At the moment, we're looking at the topic of isotopes. And this has a lot to do with the basic concept of the atom. This touches on subatomic particles. This touches on the atom, subatomic particles, because we need to talk about, in the very least, protons and neutrons. And this talks about this then also touches on the atomic number, the mass number, and atomic weight. Yeah. So let's see. The best place to start would be to say, are you familiar with the subatomic particles? How do you feel about the topic of subatomic particles?
Subatomic particles meaning like protons, neutrons, and electrons.
Exactly. How do you feel about the topics of protons, neutrons, and electrons?
I feel okay. Like I know that the protons and the neutrons are in the nucleus and then the
Okay, good.
electrons are on the outside. And that I believe neutrons are the ones that influence isotopes, right?
Precisely. Absolutely. Good. That is very good. Yes. They are the cause of isotopes. Now, how would you define, would you be able to define an isotope for me?
I would say an isotope is an atom that has a different number of neutrons than the amount of protons.
Okay, so you're saying it's one that has a different number of neutrons than protons. Okay,
Yes.
well, that's a good place to start. That is not always the case
Okay.
to begin with. For example, let's start with the definition. So, uh, to begin with, how do you feel about the topic of um, elements, different elements?
Mm, in terms of what?
Uh, if I were to say, could you define what an element is?
Maybe not.
Okay, that's a good place to start too. Then let's kind
Okay.
of touch on that a little bit too. Let's see if I can find very quickly. Uh, let's see, blah, 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 atom, et cetera, et cetera. Okay, so basically, how would you define an element would be, it is a pure substance that cannot be broken down into any more simpler substances.
Okay.
When we talk about elements, we are talking about substances at their purest level. It cannot be broken down further by chemical or physical means. This is matter at its most pure form. This is matter that literally is been isolated, and these are individual. So when you ask, so an atom, if you will, essentially an atom is the smallest unit of matter because you go below that and you get to subatomic particles. Subatomic particles are, of course, the particles that atoms are made of.
Mm-hmm.
But subatomic particles can't exist, don't do anything of interest on their own if they are just subatomic particles. Matter is fundamentally built from atoms. You can't just build matter out of subatomic particles. You have to take those subatomic particles first and have individual atoms.
Okay.
Does that make sense at all?
Yeah, no, you're making
Okay.
sense.
Okay, so we have to start by taking subatomic particles and organizing them into atoms. Once you have atoms, then you can start building larger matter. Once you actually have a single atom, you're talking about what matter is actually made of. So atoms equals matter, and basically the basic unit of matter. Another way of thinking about this now also is that atoms can have very different chemical and physical properties. So essentially, you can almost think about it as different species of atoms are what you are talking about when you're talking about elements. So when you're talking about elements, you're kind of talking about the different actual species of atoms. So a hydrogen atom versus a helium atom. They have different chemical properties.
Okay.
Okay. And the chemical properties are determined, the chemical properties of each element
Ooh.
are determined by what element, to begin with, what element an atom belongs to. And for that doesn't quite make sense. So we'll say for what differentiates atoms of one element from atoms of another element are the number of protons in the nucleus. So the fact that hydrogen has one proton in its nucleus is different from helium having two protons in its nucleus. The same goes for example, carbon to nitrogen. The fact that carbon has 6 protons in its nucleus is different from the fact that nitrogen has 7 protons in its nucleus. And that is the feature that differentiates these elements from one another. And elements literally are the purest, I'll say it again, elements are the purest form of matter. If someone says, I have a block of pure gold, gold is actually an element. So you're actually dealing with a pure element when someone says this is 100% pure gold. That is a pure elemental substance. How are we doing so far?
Following.
Following so far? Okay.
Mm-hmm.
All right. So atoms of the same element will have one, the same chemical properties in general. And I shouldn't even say in general. They will have the same chemical properties. Okay. They will have the same color. Well, okay, that's a physical property, but they will react essentially the same as other members of that same element. They will also have the same number of protons in their nucleus. And those things are linked together. And the number of protons of an element is equal to the atomic number. So the atomic number, often represented with the letter Z, is the number that gives you the number of protons for that element. How are we doing so far?
Doing good. Let's see.
Any questions so far?
No. No questions. Hello?
Yes, still here.
Oh, sorry. I thought you could
No
hear me.
problem.
I said no questions. Doing good
Okay.
so far.
Perfect. All right. So if you change the number of neutrons in that nucleus, you don't affect the chemical properties and most of the physical properties. Of the atom. All you generally affect is the atomic mass. So, in comparison, an atom with 6 protons, and we're not even mentioning ignoring the number of neutrons in the nucleus. So an atom with 6 neutrons is a carbon atom. An atom with 8 protons, that's going to be an oxygen atom every time. Okay.
Mm-hmm.
Now, take an atom with 6 protons and 6 neutrons, that's going to be carbon. If you have 6 protons and 8 neutrons, that is still going to be carbon. The number of neutrons does not affect what element you are. This will be carbon 12, referring to the mass number. And this will be carbon 14, referring to the mass number. Meaning that there's 14 particles in that nucleus compared to 12 particles. But that is due to the change in the number of neutrons. So an isotope, or I should say isotopes are atoms of the same element with different mass caused by changing the number of neutrons in the nucleus.
Okay.
How does that track?
That seems good.
Okay. My hope is that this will clarify and simplify the subject.
Yes. I
Okay, good.
understand more.
Okay, so that is basic definitions and differences surrounding isotopes. Is that what you were looking for?
Yes. Thank you so much.
No problem.
Then,
Okay,
I guess.
let's see here. We're going to resume recording. So now we're talking about chapter 4 material. Specifically, we're looking at subjects around covalent bonds. Can you define a covalent bond for me at all?
Let's see. I think it's two. It's two electrons sharing atoms. I'm sorry, right? No, two atoms sharing electrons, and they're usually metals.
Well, you are headed in the right direction. Absolutely. So let's look first at ionic bonds from chapter 3. In general, ionic bonds are formed between ions. I know that sounds like an obvious statement, but it is an important thing. So they are formed between ions. What is an ion? An ion is a charged particle, either a single charged atom or group of atoms, those polyatomic ions. And then the bond forms between ions of opposite charge. So that's part of it. Are you okay if I just move through this quickly?
Mm-hmm. Yeah, that's great.
Okay, cool. Okay, so that's the general idea. Now, ions can also be therefore differentiated into cations that are positively charged, and they get that positive charge by losing an electron. Anions, negatively charged, they gain electrons. We'll just say gain electrons because of course they can gain more than one. It's possible to gain more than one, but we'll just say negatively charged, gain electrons. Ions form because there's a transfer of electrons from the thing becoming the cation to the thing becoming the anion. For example, if you have sodium elemental with no charge and you add to it chlorine with no charge, you literally will see movement of the electron from the sodium to the chlorine, resulting in a positive charge on the sodium and a negative charge on the chlorine. Therefore, you get a sodium ion and a chloride ion. And that is how that happens. Then you end up with those positive, negative charges being attracted to each other, forming an ionic bond, pulling them tightly together. So ionic bonds are generally between metals,
Mm.
typically that are the cation, and non-metal, anion, or metals and polyatomic, or polyatomic that's positive and non-metal, or of course there's all variations on this, right? The cation positive, negative, polyatomic negative, polyatomic positive, and polyatomic negative. All of that is not really what you were asking about, but it's important to start with that to then go, okay, here's what an ionic bond is, and therefore what a covalent bond is not, right? So a covalent bond is not a transfer of electrons like this. It's not a full transfer of electrons, okay? An ionic bond involves full transfer of electrons from the thing that becomes the cation from the thing becoming the cation to the thing becoming the anion. So we're talking full transfer of electrons. Something loses an electron, something gains an electron. In comparison, a covalent bond is a sharing of electrons between two atoms to essentially complete an octet or something along those lines. But it'll be sharing. So yeah, a covalent bond is a sharing of electrons between two atoms to become more stable. That's the whole goal of all of this. But atoms are indeed shared in pairs in an, if you will, effort to fill orbitals. It's all back to that idea of stability. It's all back to that octet rule. That octet rule does come back into play. There are, of course, exceptions to that because rules can be broken, but it comes back to the octet rule, which is, of course, in general, atoms want to achieve a valence set of 8 electrons. Exceptions, yes, but the general goal is to achieve a set of 8 electrons. How are we doing so far?
Doing good.
Okay,
Oh,
so
sorry. I do have one question.
certainly.
So if they're sharing an electron and not transferring it, does that mean that atoms of similar charge are the ones that are attracted to each other in covalent bonds?
Can you repeat that, sorry?
Yeah, so since they're not fully transferring the electron, is it atoms of similar charge that are going to be attracted to each other? For example, two atoms with like 7 valence electrons as opposed to an atom with 7 and an atom with 1?
So there is a general good idea of what you have there, but keep a couple things in mind. First thing to keep in mind is there is no electron transfer, right?
Uh-huh. Yeah.
So because there's no electron transfer, this means there is no formal positive and negative charge here. There's actually no charge, no actual charge in the way that we're thinking with ions. There's no formal charge involved the way that we do think of with ions. It gets a bit more, it gets far more, in some ways it gets far more complicated, and in some ways it gets more simple. So for example, the easiest example is to start with 2 hydrogen atoms. If you start with 2 hydrogen atoms, you go, okay, we're going to put these two together. 2 little hydrogen atoms hanging out together, just kind of wanting to be more stable. Well, what happens is they decide, they kind of quote unquote decide, which is all, there's no decision making involved. But what happens is, it turns out that so these hydrogen atoms have electron clouds around them, right? And it turns out that if they decide to, if they get within a certain distance and overlap those electron clouds, it can actually allow them to be more stable. So they overlap their orbital clouds and then share these electrons between them. And that sharing of electrons between the atoms, what this actually does is this allows each H atom now has a full valence shell, because for hydrogen, having a full valence shell is having 2 electrons. And, well, okay, that's not the only truth, but in this situation, having 2 electrons completes the full valence shell for hydrogen. And this is achieved by sharing. So each atom doesn't lose an electron. It doesn't actually fully, each atom does not at all lose an electron. Each atom also does not fully gain control solely over either atom. Instead, it's almost like 2 parents being equally responsible, especially in this situation. These are 2 parents who are equally responsible for their little electrons.
Okay.
Now, does that make any sense?
Yes, it does.
Okay. Now, let's look at something along the lines of chlorine. So chlorine, if we draw a electron dot diagram of the valence electrons within chlorine, chlorine has 7 valence electrons. Does that make sense? If I say chlorine has 7 valence electrons, would you be comfortable with that?
Yes.
Okay. So chlorine has 7 valence electrons. Now, all chlorine needs then is to share those electrons, again, just like hydrogen did. Each one just needs to share 1 electron to form a bond between those 2 chlorine atoms. And when that happens, each chlorine atom then appears to have a whole octet, because once you have 1 electron now shared within your electron, your outer valence electron cloud, you now complete that electron cloud. What this also means is a bond is formed when you have a pair of electrons shared between two atoms. So a bond is literally the overlap of an orbital, 2 orbitals, 1 from each atom, sharing, therefore, those electrons between the 2 atoms, and that becomes the bond. So a bond literally is a sharing one electron usually from each atom. So it's a sharing of one electron from each atom into a bond of two shared electrons between the atoms. Does that track for you?
Yes.
Okay.
Okay.
So is there anything that's not making sense for you?
No, not really. So again, I'm going to try to rephrase my question.
Please.
So I understand that they transfer, there's no transfer of atoms in covalent bond, they're just sharing.
Correct.
So my question is, does the number of valence electrons that an atom has in its shell, like for example, these two chlorine ones, so they both have 7.
Yes.
Is that why they form a covalent bond? Because they both only would need to share like one more to have
Precisely.
an octet?
Yes. But that's not
Okay.
the, I mean, that is why in this case they each form, they participate in the single bond between the two chlorine atoms.
Mhm.
It's not the only type of bond that can form. And bonding is not that simple. For example, if you bring in a carbon atom, which will have 4 valence electrons, like so, and you add to that 4, we can say chlorine atoms, which are each looking for a complete octet. So carbon is looking for 4 octets. If you look at carbon carefully, carbon needs, not 4 octets, sorry, 4 pairs of electrons to get that complete octet. Whereas again, chlorine, as we saw in the previous example, just needs one more shared pair to get an octet.
Okay.
And so because of that, each chlorine, we start with carbon. So carbon, and essentially the easiest way typically that we look at this is we put carbon then at the center, and carbon is going to pair with 4 chlorines, because again, you can only put 2 atoms into a bond. So you can form a bond here. You can take another chlorine atom and form another bond here. Another chlorine atom, form a bond there, and finally one last chlorine atom and form a bond there. And so that gives you, now you can see carbon has gained 2, 4, 6, 8 valence electrons now that it's sharing 4 electrons from 4 different chlorine atoms. And each one of those chlorine atoms now has a complete octet because it has now gained a shared electron from carbon.
Mhm. Okay. Yeah, that definitely answers my question.
Okay. Now, let's look at a couple of other examples of things like this, because what happens when you bring 2 nitrogen atoms close to each other? So nitrogen looks like this.
Right. Yeah.
Like so. This is nitrogen. And ultimately what we're going to form is N2. But how does that actually happen? Well, what actually happens is 3 different pairs of electrons get shared between these nitrogen atoms. Like so. And that is how you end up with one of the most stable substances around us, diatomic nitrogen. There we go. Diatomic nitrogen, or just N2. This is essentially the structure of diatomic nitrogen. It's got a triple, what we actually consider what is called a triple bond, which is 3 individual bonds that overlap such that you get a triple bond.
Mm. Okay. That makes sense.
Okay, good. If that makes sense, the next thing to look at, well, there's a bunch of different things to look at, of course. But I can keep showing you examples of this, or do you want other topics in the remaining 10 minutes?
Let's see. No, I can't think of any right now.
Okay, then I can ask your classmate who's actually come into the classroom. Do you have any questions? Okay, because you're welcome to ask questions. If I happen to get here early, you guys are welcome to ask questions while I even hold an office hour online. You're allowed to participate. You bet. No problem. Okay, let's see. So we've talked about the general idea of orbital overlap, covalent bonds or sharing of electrons. We've looked at a few of these structures. We've even technically actually looked at a few Lewis structures. That comes down to then a number of things. I'll say it again. Bond formation. Now this is very general. Bond formation is all about atoms trying to reach more stable, which means actually lower energy states. So it doesn't matter whether we're talking about the formation of an ionic bond, whether we're talking about the formation of a covalent bond, or actually there's a thing called a metallic bond as well, which is just between metals. Whether we're even talking about metallic bonds, it's all about a sharing of electrons in an effort to lower that energy state of the electrons, typically to gain a valence electron octet in some fashion.
Mm-hmm.
Since we're continuing to talk about covalent bonds, in the now, well, time's flying by, of course. If we're talking about covalent bonds, there are single bonds, double bonds, and normally we only talk about single bonds, double bonds, and triple bonds. There may or may not be other types of bonds that I'm not going to disclose that information. I will say that that is classified information.
Okay.
Just jokingly. A single bond is, of course, a pair of electrons shared. A double bond is 2 pairs of shared electrons, and a triple bond is 3 pairs of shared electrons. The important thing to understand about that is that it's easy to think about a double bond as being just a individual unit. And yes, it is an individual unit. The way I like to think about this is if you have two cities, so you've got city A and city B. You can connect those two cities by a single road. And that'll be called a one-lane road. You can connect that city by a two-lane road, but now that two-lane road has two lanes. You can connect that city by a three-lane road, and that's just one road. So that's like a single lane road, a double lane road, or a triple lane road. But that also means that each one of those lanes is an individual unit. Does that make any sense?
Yes.
So that one road is still made up of now two lanes versus a single lane versus a triple lane. And each lane will be driven down, of course, by a single car. And you can think of the single car as in this very bad analogy, a pair of electrons. Each lane represents space for a pair of electrons to exist in.
Okay.
All right. Okay, cool. Let's see, what else can I say? Do you guys have any questions? No? Okay, no problem. I'm just trying to find more material also here. Let's see, what else? What else? 5 minutes left.
We can end it here if you like.
Okay, I mean, if you don't have any questions and you feel like you've gotten some very good material out of this, which I'll pretend that is clear.
Yes.
Then we will stop here. And I hope this was helpful.
Thank you.